Hi, it's Mr. Baker here, and today we're going to be looking at centripetal acceleration. So we're going to be looking at centripetal acceleration today, and we're going to be finding out what it is. What is centripetal acceleration? So we're going to do something you probably don't actually need to do. You don't need to be able to derive the equation for centripetal acceleration, but I think it's quite interesting for you to be able to see where it comes from. So I'm going to go through the derivation of it, and then you're going to be able to see what the equation is. And then hopefully by the end of today, what you need to be able to do is be able to know what the equation is and be able to use that equation. Okay, but I'm going to go through it. So let's imagine that we've got an object traveling around a circular path like this one. And it's going around a circle with a radius r. If it's changing direction, then its velocity must be changing. Remember, our definition of velocity is that it's speed in a given direction. And so if the direction's changing, then its velocity must be changing. If its velocity is changing, then that's what we call acceleration. So it must be accelerating. Remember, that's our definition of acceleration. It's the change in velocity divided by the change in time. So at any point, it's going to have this instantaneous tangential velocity. So it's coming off. If I let go of that object, say I'm twirling something around my head, and I let go, it would fly off with that velocity in that direction, just straight off. So after a time, delta t, it would travel a displacement s. Okay, so it would go around part of that circle, part of its circular motion, and it would just travel around that portion of the circle. And it would have gone a displacement s, although its distance would have been the going around the perimeter of the circle, its displacement would just be from that point to the point that it ended up at. And at that point, its velocity would be going off in that direction. So at time 1, you can see I've got a velocity going off in one direction. At time 2, my velocity is going in a completely different direction. So at time 1, the vertical and horizontal components of v could be shown as v cos theta for the horizontal component and v sine theta for the vertical component. And I've drawn the little diagram at the top there. Okay, so just take a moment, just make sure you're happy with that. And this really comes from the fact that cos theta equals the adjacent over the hypotenuse and sine theta equals the opposite over the hypotenuse. And so we can use that then to find out what our horizontal component and our vertical component would be. Okay, from those. So the adjacent would be the hypotenuse times cos theta, and the opposite would be the hypotenuse times sine theta. And so if we draw our angle like we have, then the horizontal would be the adjacent, so we would have v cos theta, and our vertical would be the opposite side, and so we would have v sine theta. Okay, so moving on. At time 2, the components can be found in a similar way as before. And you can see that the horizontal component of the velocity hasn't changed. So v cos theta is the horizontal component in both of those times. At time 1 and time 2, v cos theta is the horizontal component. But the vertical component has changed. And it's changed from this, it was going up basically, v sine theta going straight up at t1, to this. At time 2, it's going straight down. So it's labelled there minus v sine theta. So in other words, the size of the change is going to be 2v sine theta. Okay, so v sine theta minus v sine theta equals 2v sine theta. Okay, so the change in the vertical component is 2v sine theta. Okay, again, just take a moment, just make sure you can work through that and that you're happy that I haven't just made that up. So our delta v, the change in velocity, is going to be 2v sine theta. Okay, right. The vector triangles and the triangles shown in the diagram are similar. So those triangles that I've drawn and the triangles that I've drawn on the circle are similar triangles. So the sine theta equals opposite over hypotenuse. We're happy with that. So if sine theta equals opposite over hypotenuse, then the opposite for this triangle in the circle is going to be s over 2 divided by r. Okay, hopefully you're happy with that. Or I could write that another way. Sine theta equals s over 2r. So I've just put the 2 down the bottom there. So remember our definition of acceleration? Hopefully you do. Acceleration is the change in velocity over the change in time, delta v divided by delta t. So delta v equals 2v sine theta. That's what we've just said it is. Yeah, that's what we just derived. And so our acceleration then, if delta v is 2v sine theta, is going to be 2v sine theta divided by delta t. So acceleration equals 2vs over 2r delta t, since sine theta equals s over 2r. So I've just substituted sine theta in there. So where I've got sine theta there, I've just substituted in s over 2r, and so I've got s over 2r instead of my sine theta there. And then I can simplify that a little bit further. If we say that the velocity is the displacement over the change in time, then we can say that acceleration is going to be 2v squared over 2r. And again, I can simplify that again. Acceleration equals v squared over r. Okay, so this is an acceleration that is happening for an object travelling in a circular path. The acceleration equals v squared over r. And this is our equation. So this is the equation that you need to know. Like I said, you don't need to know the derivation of how we got here, but I think it's quite interesting that you could follow through with all of that maths. But again, if you are working through that and you get a bit lost, then don't worry too much, as long as you are happy to accept that in a circle the acceleration, the centripetal acceleration, equals v squared over r. Okay, so this is our acceleration for an object following a circular path. So something that's going around in a circle will have an acceleration of v squared over r. So how are v and omega linked? Can you remember from what we've done before? So we've got the angular velocity, omega, and the instantaneous velocity, v. How are those two linked? So hopefully you can remember that v equals omega r. So if v equals omega r, then I could write a equals omega squared r, couldn't I? So I could put in my v, for v at the top here, I could put in omega r, and that would be omega squared r squared. So omega squared r squared over r, acceleration equals omega squared r. So I've got two equations now for centripetal acceleration. I've got a equals v squared over r, and I've got a equals omega squared r. Okay, so that's the end of this one. This is what I think you should be able to do at the end of this. You should be able to state the equation for acceleration in a circle. You should be able to use the equation for acceleration in a circle, so you'll need to do a little bit of practice on that. And then some of you also might be able to derive the equation for acceleration for an object moving in a circular path. So acceleration in a circle. So what is centripetal acceleration? Because something that's travelling in a circle is changing its velocity, because it's going to be changing the direction it's going every instant. Something that is changing its direction is going to be changing its velocity. If it's changing its velocity, then it must be accelerating. And then we've come up with a little equation to show that. Okay, that's that today. I've been Mr. Baker, and I'll see you next time. Thank you.